Alright gang, here we go. So this is Physics, Unit 3. We're going to be starting, this unit covers two different chapters, Chapter 5, which is about work and energy, and then Chapter 6, which is about momentum and collisions. So it should be a pretty fun unit. Okay, let's see here, press the wrong button. Alright, so in class, to start, like, we're going to be talking about work. Okay, so if you think about things, just pause it for a moment and think about things that you would consider work that you've done in the last week, right? Because one of the tricky things about this specific unit, especially this specific chapter, is that there's going to be several terms that we use in physics that are very, very similar to words that you use every day in real life, but they have slightly different meanings. Okay, so you need to make sure that you understand the difference between the real world example for that thing and then the the physics definition for these things. And so work is the first one, right? So you might think, well, I worked on my homework last night. You sat at your desk and you did your physics homework or whatever it is that you did. Okay, so that might be considered work, right? And so just try to come up with the definition just in your head a little bit. Okay. Now, in physics, the way we define work, it's defined as the magnitude of the force. Okay, so remember, magnitude means you see magnitude and you should think absolute value. Okay, so it's the absolute value of the force times the magnitude of the displacement. Okay, so it's really force times distance. Force times distance. Okay, but it has to be the distance that is in the same direction as the force. All right. Now that's a big key, okay, and we'll do a practice problem later on where we have to analyze if the force and the displacement are in slightly different directions. How do you approach that kind of problem? But in physics, the basic definition is defined as the force times distance. So picking something up and moving it would be work, right? But just holding something in place in physics, that's not work, okay, because it did not move. Okay, all right, so here's your formula. Work equals force times distance. Okay, and we'll get a little bit more in depth in that here in a second. The units that we use for work are joules, and we've used joules in the past. In chemistry, we used joules when we talked about the energy in a chemical reaction, so on and so forth. Okay, but here we're talking about joules, and we specifically are talking about them in terms of newtons times distance, or Newton times meters, Newton meters. Okay, and remember it's force times distance, and force is calculated in newtons, and distance we use meters because that's the SI unit, so that's where we get like this combination, Newton meters for joules. All right, so whenever you calculate work, the unit that you use is going to be joules. All right. Work is a scalar. Now remember, scalar means that it has a magnitude, positive or negative, but it doesn't have a specific direction. Okay, so we don't worry about like the angle that the work is being done in. It's all in relation to the displacement or the force that's being applied. Okay, so negative work. So notice that this guy's pulling this toy car. The toy car is going to the right, but he's slowing it down a little bit by pulling on this thing here. Okay, and so this would be negative work because the work being done is in opposition of the force being applied. Okay, same thing here. See so the work being done, remember, force times distance. So the distance is going this way, but you're doing work to try to stop it going that way, but it still end up going that way. So these are both negative work, whereas on this side we have positive work. Okay, where the work and the displacement are happening in the same direction. So these would be positive values for work, and these would be negative values for work. So the sign of the work, okay, is important. All right. And essentially what this means is that if your work and your displacement are in the same direction, that means whatever object you're working on is going to be speeding up. Okay, and then if your work and the displacement are in opposite directions, one's positive, one negative, then they'll be slowing down. Okay, same kind of idea as acceleration and velocity when we talked about that a couple units ago. All right, so let's just talk about a couple of things here. So would pushing a car be considered work? Well, we're pushing it, right? And let's just assume that it moves. Okay, so you're applying a force in this direction, right? And then the car is moving in this direction. So yeah, that would be work, because you're applying a force and it's going a specific distance. Okay, so yeah, that's work. Holding a heavy weight at arm's length for several minutes. So it doesn't say this heavy weight is moving. We're just holding it out there. Now let's think about this. Okay, remember, work equals force times distance. Now your force here. Okay, your force, yeah, you're applying a force, yes, you definitely are, right? It takes energy in order to hold that heavy weight out there, but is it moving? No, it's not moving, so therefore the work has to equal 0. Okay, so this guy, no, this is not considered work by the physics definition. Real world definition, for sure, this is work, right? But physics definition, this is not work. All right, a student carries a bucket of water along a horizontal path while walking at a constant velocity. Now let's think about this again. Work is equal to force times distance, okay? And so we're carrying it, okay? So yes, the distance is moving. But let's think about force for a second. If we think about force, what's our formula, like our basic formula to define force? Well, it's F equals mass times acceleration, okay? Now let's think about this. So our bucket of water, does it have mass? Yes, it has mass. But is it accelerating? Now acceleration is defined as a change in velocity. Okay, so if we don't have any change in velocity, then we don't have an acceleration. So therefore, okay, so it says it's a constant velocity, right? So therefore, our acceleration is 0, which means our force has to be 0, which means this is 0, which means we have no work going on. Okay, so that's pretty tricky, right? So you think about this, let's just go through it one more time. So it's a student carrying a bucket of water along a horizontal path while walking at constant velocity. All right, so yes, it's moving. Okay, that's the distance part, but the force part, is there a force that's being applied? Well, no, there is not a force being applied because you're moving at constant velocity. All right, constant velocity implies that your acceleration is 0, and because F equals ma, if your acceleration is 0, therefore your force has to be 0. Okay, all right, so no, there's no velocity there. All right. Now let's think about this. All right, work, remember, work is equal to force times distance. I'm just going to, you need to have this guy. This guy's going to be memorized by the time you're done with all this. Work equals force times distance. But remember, these two things need to be in the same direction. Okay, if they're not in the same direction, then our formula doesn't work. Okay, so what happens if our displacement, so say you've got a crate and it's on this floor, and you're like somebody, this crate's really big and whatever, and so some really small person is sitting there pulling on this crate, this giant crate, right? And since you're not tall enough to pull it straight across in the direction of the displacement, you're pulling at an angle. Okay, so you have to think about, well, I really don't care. Remember, this force is divided into two components, right? We've got a horizontal part of our force. We got a vertical part of our force. Yeah, you thought you were done with vectors. No, I told you they'd be important. So we got some force in the x direction and some force in the y direction. Now, we don't really care about what's pulling it down because the floor is going to stop it, and we're displacing directly to the right. So the only thing we care about is this f of x, right? This displacement in the x direction, or the force component of the force that's being applied in the x direction. Okay, so if we think about this, remember, so our theta, our angle is right here, okay, and we know that the cosine of theta is equal to, in this case, f of x over the hypotenuse, which is just regular old f. Okay, so our f of x is going to be equal to, f cosine of theta. Okay, let's erase so it's nice and clear here. Just got rid of the whole thing, didn't it? All right. So f. All right, f cosine theta. All right. So if we wanted to figure out the work that's being done here, we really only care about this guy. So our force would have to be this thing because we only care about the f of x portion of it. So it really becomes f of it would just become f cosine theta d. All right, so we would calculate work as work equals force times the cosine of whatever angle we're pulling at times the distance. Okay, now that's the formula you need to memorize. So let's analyze this real quick. If our angle is 90 degrees, what is the component of F in the direction of D? Okay, so let's just sketch it out. So we've got D, and it says it's 90 degrees. All right, so this is our theta that's going like this. All right, so this is our F, this is our D. Now let's think about this. So this is our component. So if we're pulling straight down, that's where 90 degrees is. Or it could be straight up, right? It could be straight up. Either way, if it's 90 degrees, what component of our F is pointing in the direction of D? Well, none of it is, right? So since none of it is, and you can test this by plugging into your calculator, if you plug cosine of 90, okay, cosine of 90 in your calculator, you'll actually get 0. Okay, and those of you in trig or calculus, this is pretty obvious to you. So if our force is being applied directly perpendicular to our displacement, then there is no work being done. Okay, now let's think about another case. All right, that what if our angle is 0? All right, so that means our displacement's this way. Okay, and then also our force would also have to be this way. Okay, and so this angle here is 0 degrees. Okay, so we can plug that in. So cosine of 0, well, that just equals 1. You can punch that in your calculator, double check, and just make sure that you're in degrees when you do this. Okay, when I say that, and if you don't know what I'm talking about, please come and talk to me. Okay, so F cosine theta is equal to F. Okay, so if so we can always use this formula here. Even if they're in the same direction, we just plug in 0 for our theta, and it all works out. So here's our big overarching work equation. All right, the F net. So this is the net force times the distance times cosine theta, and the theta is the angle between them, is kind of vague, between the displacement and the force. Okay. All right, so let's try this here. A 20-kilogram suitcase is raised 3 meters above a platform. How much work is done on the surface? Well, we know work is equal to F net cosine theta times distance. Okay, it's raised 3 meters above a platform. How much work is done? So the displacement. So if we're raising it this way, so that's the displacement, and it's 20 kilograms. Okay, so we need. Right now we just have mass and that guy there, right? So let's think about this. What else do we need to solve for then? Okay. All right. So we have a 20-kilogram suitcase, and it's being raised 3 meters above a platform. So let's think about what needs to be going on here. So we've got, we know that we have the displacement portion, but we need to find the net force. Okay, so we know that the force is equal to the mass times the acceleration. All right, well, the mass is 20 kilograms. All right, so our F is equal to 20. Okay, but what's the acceleration? Well, the acceleration has to be 9.81. Okay, yeah, because it's moving up and down, so that's the acceleration due to gravity. So if we take 20 times 9.81, and then we'll get 196.2, and this is in newtons because that's our force. And then if we take that guy here and we plug it in for our or we take that, so this is our F net, right? This is our F net. Okay, and our theta, well, what's our theta equal to? Well, our theta, since these two things are in the same direction, our theta is going to be equal to 0 degrees. All right, so now we can plug this guy in. So our F net is 196.2. Okay, our cosine is 0, and then therefore our displacement is the 3.0 meters. Okay, so if we plug that in, we take 196.2 times cosine of 0 times 3, and we get 588.6. And it's in work, so it'd be joules. Now let's think about this. How many sig figs? So this guy has 3, and this guy has 2, so we have to round to 2 sig figs. So it becomes 590 joules. Okay. Cool? All right. So here you can list, take a second and think about 3 examples of work that you have done in the past week according to the physics definition. So at the start we talked about 3 definitions of work that you have from your own real world experience with work, and then now that we've beat the bush on work, come up with 3 examples on your own. Okay. In this video we're also going to talk about kinetic energy. All right. So you should already be familiar with these 2 factors of kinetic energy, or these 2 factors of energy, both kinetic and potential energy. Okay, kinetic energy, all right, is energy of movement, right? Okay, so it's how much energy something has as it's moving. So it's got some sort of velocity, it's going somewhere, it has some sort of energy. Potential energy, you've probably discovered, is the let's see, what's the common definition that everybody, the energy, the capability of doing energy or something like that. Capability of doing energy. Okay. And you should know that the factors that affect kinetic energy, you should be aware that mass affects kinetic energy, and you should know that velocity or speed affects kinetic energy. All right, and then with potential energy, probably the only one you're familiar with now is that when things are higher up in the air, they have more potential energy. So you really should this is probably all you're familiar with right now, is height. Okay, another one that we're going to talk about as far as potential energy goes is like if you're pushing against a spring. All right, so the strength of a spring, because that's going to have some sort of potential energy as well. All right. Alright, so this here, you don't really need to know how to do this, but I thought it was interesting, so I included it here. And this is relating kinetic energy and work force. Like, you should be aware that kinetic energy, you should probably be aware that this is the general formula for kinetic energy, right? Kinetic energy is equal to 1/2 the mass times the velocity squared, or speed squared. Okay, so what can we relate these two? Okay, well, we know that from before that the work is equal to force times the distance. And if we replace force with mass times acceleration, we know that work equals mass times acceleration times the displacement. Okay. We also know from our kinematics that this is true. Okay. And you can see that A delta x is here, and it's also up here, right? So we can take these guys here and plug them in. Okay. And then they just kind of rejigger this around in like 3 or 4 steps. So then that our work net is equal to the mass times velocity squared minus velocity initial squared divided by 2. Okay, and it's really like this whole thing is divided by 2. There's a parentheses missing right here. Okay, yeah, we'll get rid of that in parentheses. Okay, anyway, so that comes out to be this guy right here, and you should recognize, well, heck, that's 1/2 mv squared, and this is 1/2 mv squared. Okay, so our work is really just the change in kinetic energy, right? Because this is the final minus the initial. And you know that anytime you see delta, remember when you talked about change in velocity, it was really just the final velocity minus the initial velocity. Remember that? Okay. So anyway, so here's kinetic energy. There's the general formula, and you already know that kinetic energy, because it's an energy, we calculate it in joules, same as work, 1/2 mv squared. All right, and then the work kinetic energy theorem, that's what we just derived. Okay, and it says that the net work is equal to the change in kinetic energy. Okay, or you could also think about it as the kinetic energy final minus the kinetic energy initial. All right, so this is the change in kinetic energy. All right, kinetic energy is the work an object can do if the speed changes. All right, so this is what happens. Like if our speed is changing, then we'll have 2 different kinetic energies, one initially and one finally, and we can subtract them. Okay, if the speed increases, our work is positive, and then if W net is negative, the speed decreases. All right, pretty sweet. All right, let's do a couple practice problems and call it a day. All right, a 6.00 kilogram cat runs after a mouse at 10 meters per second. What is the cat's kinetic energy? Well, we know kinetic energy is equal to 1/2 mv squared. Okay. All right, so we take 1/2, and we know the mass of the cat is 6 kilograms, so 6.00, and we know that the velocity of the cat is 10. All right, 0.0. So this becomes 3 times 10, which is 30.0 meters per second. Oh, no, what am I doing? The 30.0 joules, because it's kinetic energy, not meters per second. All right, so there's the kinetic energy of the cat. All right. Did I do that right? Oh, you know what? That can't be right. You're all sitting there yelling at me saying, Mr. McLeod, you didn't square it, did you? Okay, so it would be square 1/2 times 6, so 3 times 100. So that would be 300. Let's see. Oops. So it'd be 300. And then we'd have to put a line here to represent that that's the significant digit. Oh, there's 3. So that would be, shoot, dang, I'm just fouling this up all over the place, aren't I? So we could put a line there to represent that that's a significant digit right there, or we could put, we could also say 300 with a decimal for joules, or we could be super fancy and say 3.00 times 10 squared joules. All 3 of those would be exactly the same value. All right. Then it says, suppose the above cat accelerated to a speed of 12 meters per second while chasing the mouse. How much work was done on the cat to produce this energy, or this change in speed? All right, so remember, work is equal to the change in kinetic energy. Okay, so this is the kinetic energy final minus the kinetic energy initial. All right. Well, the kinetic energy final is going to be equal to 1/2 the mass times the final velocity squared minus 1/2 the mass times the initial velocity squared. Okay, so this would be 1/2 times the mass. So the mass of the cat is 6.00 kilograms. The final velocity is 12 meters per second, right? Because he accelerated to that speed. So it'd be 12. Now don't forget that square, otherwise you'll look like a fool on YouTube. All right, 1/2 6 times 12 squared, and then we'll subtract out the initial information. So that's 1/2 times the mass times, and the mass is still the same. It's still 600. Okay, I guess I really don't have to solve this because we solved for it in the last slide, but I'll throw it in there anyway just in case you might have skipped it or something. So 6.00. All right, and then the old velocity, what was the old velocity? 10? Yeah, it was 10. And don't forget to square it. All right, so this becomes 3 times 144 minus 3 times 100. Okay, we can pull those 3's out. So it really becomes whatever. We don't need to be fancy with this. We can just plug it in. Right? 3 times 144 minus 300. We get 132. And because this is work, our units are in joules. Check our sig figs. Everything's got 3. So we're ready to roll. And that's it. 132 joules is the work that was done on the cat to produce that change in speed. Okay. Anyway, so that's it for this. We'll talk about potential energy in the next video. So do your practice problems. Don't forget those text practice problems that I included. You really need to do those before you do the checkpoint. It'll help you a lot. All right. So anyway, do your practice problems. Come see me with questions, and I'll see you on the flip side.